Refraction is defined as the slowing down of waves or speeding up. It's a change of speed in the wave. Along the way, there might be some bending. So let's just take a look. We've got some fast long waves coming along. As they get to shallower water, they encounter extra drag or resistance or friction at the bottom of the wave, and that slows the wave down, and in turn shortens the wavelength. If we look at V is equal to lambda F, remember, frequency is the birth of the wave. That's the beginning. It can't change. The waves are coming at a certain rate. Boom, 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 boom. And I made the rate over here. So I can't change the frequency later on the wave. Therefore, if I'm going to slow that wave down, I must also shorten that wavelength in order to keep the equality sign. The wavelength shorten and the waves slow down when they enter the shallower water. The amplitude stays the same, so that remains the same, and the frequency stays the same. So if we're going to watch a video of this, you can see we've put a little block in there to make the water a bit shallower at that. And if we're going to watch that, you can see that here your waves are bending a little bit. So they're coming in straight. And I'm going to play that again in a second, but they come in, you can certainly see the wavelength over there versus the wavelength over there. In the shallower area, it is definitely a shorter wavelength. The other thing is you must watch how the wave bends. It doesn't bend on this particular slide because of the fact that it is coming on straight. But the minute I put an angle onto that, you get a bending effect over here and a bending effect over there as the wave goes through. So refraction is the slowing down and sometimes the changing of direction of the waves as they enter shallower water. Obviously the converse is true if they go into deeper water. So we've got a diagram here. Here are my incident waves, and as it goes into the shallower water, they bend, and look, the wavelength gets smaller. Now, if we look at it in an animation, and as I said in the last video, animations are always best because they always clearly show everything as it should look. So here come these waves. They bend and get closer together. Bend and get closer together. Bend and get closer together. Again, we have got two angles. That would be a normal at 90 degrees to the surface. This will be my angle of incidence. This will be my angle of refraction. We'll look at that in a bit more detail with light. They don't normally examine it in terms of water waves. So let's look at light. Light simply refracts as it goes from one medium to another. When it goes from a less dense to a more dense medium, it refracts what is known as towards the normal. In other words, the bending goes towards the normal. However, if I went in the opposite direction, let's say I brought a light ray up from this direction here, put a little normal in over there, I would refract away from the normal. So that's if the light ray was going upwards. Light is bent or refracted when it passes through media of different optical densities or different densities. Here the light is refracted as it passes from the less dense air into the more dense medium of water. There's also a slowing down. The angle between the incident ray and the normal is the angle of incidence. The angle between the refracted ray and the normal is the angle of refraction. Notice once again my normal is drawn at 90 degrees to the surface at the point where the light ray strikes. So let's just take a quick look at some light rays shining through. As I change the surface, you can see how the light rays go. When they go straight through, they've slowed down, but they have gone straight through over there. I'm going to play it again. I then put the surface at a angle, and I could draw a normal at 90 degrees to the surface. So as good as it gets with the stylus. And that is my angle of incidence, and that is my angle of refraction. They are not equal to one another. The wave has gone through here from air into something, so it has gone from a less dense to a more dense medium. As the light ray goes from a more dense to a less dense medium, it refracts towards the normal. In other words, the angle of refraction is smaller than the angle of incidence. As it goes from a more dense medium into a less dense medium, it refracts away from the normal. In other words, the angle of refraction is greater than the angle of incidence at the second surface. So with this, if I go through a rectangular glass block, you can see that's my first surface, that's my second surface, incident ray, refracted ray. The refracted ray from the first surface becomes the incident ray of the second surface. And then we call this either the refracted ray of the second surface or the emergent ray. It comes out. What's important to notice is that if I've got a rectangular block, that incident ray and that emergent ray are parallel to one another. And therefore, what can we say? We can say that the angle of incidence at the first surface is equal to the angle of refraction at the second surface, and the angle of refraction at the first surface is equal to the angle of incidence at the second surface. In other words, that angle and that angle are equal to one another. So let's just watch a little clip on that. There, you can see quite clearly that my light ray is coming in. It is refracting towards the normal and then away from the normal again. I've now made the angle bigger and I've got a much clearer indication of going towards the normal and away from the normal. If I were to draw normals in, there's where my normal would be. And as you can see, it goes straight through. It does change speed, even though it looks like it's going straight here. It does refract in the sense that it is changing speed. It slows down and speeds up again. You don't have to study refractive indexes, but it is interesting to notice that different substances have got a different refractive index. The refractive index of diamond is the speed of light in air versus the speed of light in diamond. Look how much slower it is in diamond because it's more dense. It's kind of like if you were trying to swim in honey. The light's trying to get through a much more optically dense medium. And so that gives us a refractive index. And you can see quite clearly space and air have a very similar refractive index. Water's a bit higher, glass a bit higher, and diamond is the highest refractive index of those ones listed. Refraction of light takes place when light enters a new optical medium. The ray changes speed and often changes direction if entering at an angle to the boundary between the medium. Okay, the speed happens no matter what. The direction only takes place if there's an angle. A light ray slows down on entering a more dense medium and speeds up when entering a less dense medium. On entering a more dense medium, the incident ray is refracted towards the normal and away from the normal when it is entering a less dense medium. Now we're going to look at something called real and apparent depth, and you're going to have to be able to draw diagrams on this. So let's say I put a coin at the bottom of a basin of water, and you look at it through the water. It kind of looks like it's shallower first, and secondly, it's often displaced as well. And why is that so? Watch carefully. The light rays go from the coin. Our eyes don't send out beams of light. No. The coin gives light off. It bends at the surface, but our eye thinks that it's coming in straight lines. So our eye brings those lines back, and because of the bending, it appears shallower. This is an image. My real depth is to the object. My apparent depth, pretend depth, is where I think I see the coin. So the coin appears closer to the surface than it really is. We're going to learn how to draw diagrams on this. You're always going to draw the object first, draw the rays from the object to the boundary, refract the rays at the boundary, draw rays to the boundary to the eye, extend the eye rays backwards till they meet, and draw an image. Let me show you what I mean by that. So the first thing I'm going to do is I'm going to put a coin in. There's my water surface. I send two rays up. They get arrows. They are moving from a more dense to a less dense medium, and therefore they are going to refract away from the normal. But difficult to do this without a ruler, but anyway, if I had a normal in there, it would be about there and about there. They're at 90 degrees to the surface. And then my eye would be over there. And then I dot these lines backwards, and I find that I get an image shallower and off to the side. How about if I do this from straight above? So put my coin over there, take 2 rays up to the surface, then refract them both away from the normal, and my eye is over here, straight above. Dot these rays backwards. I find that I will get an image that is just shallower. It doesn't actually move to the side the way it does if there's an angle. And that is why if a bird like a kingfisher is trying to catch a fish, it will hover directly above the water and then shoot down, because it will catch the fish if it goes in that direction. If it was at an angle, it would go hover, 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 and it would never catch the fish because there's no fish at the end of that. But there is a fish if it comes straight down at the end of its dive. What about the other way? What if I was a fish looking at a person on the water? It's edge. So now the person gives off 2 light rays, chunk, chunk. Notice I put arrows on them. There's normals. And now we refract towards the normal and towards the normal. And here's my fishy with its eye. And we are going to take those lines backwards in straight lines. And we find that this fish sees the person much further away, and again, it's instead of being further away and displaced to the side and shallower, it's further away, but instead of being further out, like this one's further away from the eye if you consider the horizontal plane, this one's closer considering the horizontal plane. So you can do it in both directions. Notice in each case I drew an object first. I drew the rays from the boundary up to the boundary, up to the boundary. I then refracted the rays away from or towards the normal, depending which direction we were going in. Then I extended the rays from the eye backwards until they met again, and then I drew an image.